Okay, first of all, there's a bunch of definitions in this unit that we need to talk about, and let me unfreeze that so it actually will go. There we go. There's a whole lot of definitions. I'm going to try to go through them fairly quickly because you know how to read, and I'm going to try to comment what I want you to know out of that. So first of all, energy, that's what thermodynamics is the study of the energy changes associated with reactions. And we are just going to be doing the heat portion in Thermochem. And then next semester when we do thermodynamics, we'll add in entropy, which is chaos, disorder, and we'll add in Gibbs free energy, and then that's how you truly determine if a reaction is thermodynamically favored or not, okay? But energy, of course, is defined with the ability to do work, produce heat, do work or produce heat. The sum of all potential and kinetic energy in a system is known as the internal energy of the system. In terms of the ability to do work, that's usually when we're talking about gases. For the sum of the potential energy, that's going to be your bonds. That's where potential energy is going to come from your chemical bonds. And then, of course, kinetic energy is not also very lovingly known as the energy of motion. So that's where your temperature of particle movement. So that's where the kinetic energy is coming from. That's terrible. I can't even see that. That says particle movement. Apologize for that. Put my glasses back on. Okay. Potential energy, of course, is by virtue of position. That's when we're talking about the bonds. It's usually going to be stored in the bonds. And when this is where AP Bio does it a little bit differently. We're telling you when bonds are separated, it takes energy to do that. Okay, we have to put energy into the system to break the bonds, and that is to overcome something called Coulombic attraction, which is not something that you've heard of, but by the time that we get to the AP exam, you will be talking about Coulombic attraction all the time, because it is how we explain a lot of things, and it has to do. I'm not going to show you the formula for this unit. Just want you to know that that's what it's going to overcome, because we'll get to it. But basically, it takes into account the charges of the ions and the distance from the nucleus. So we'll start talking about that more. But the Coulombic attraction is what you're trying to break when you break a bond, and it takes energy to do that. Okay. So when an atom actually bonds, what happens is the Coulombic attraction results in energy being released. Nature likes things in its lowest form of potential energy. That's why it forms bonds. Okay, when it's not bonded, there's a whole lot of potential energy, and so when they bond, they release some of that potential energy, and then it's in a lower energy state. And nature tends to be towards the lowest possible energy that it can be. Okay. So here's a visual of that, of what exactly is a bond, and it's when the optimum distance is reached between two atoms to minimize that potential energy. Okay, so energy is released when the bond forms, but it is absorbed in order to break the bond. You gotta put energy in the system to break it. Okay. Kinetic energy, of course, is the energy of motion. That can be translational, rotational, and vibrational. For us, we're really worried about the vibrational because we're talking about movement of particles. It is proportional to the Kelvin temperature. And then, of course, you already know the formula, Ke equals 1/2 mv squared. And that brings us to the law of conservation of energy, stating energy can't be created or destroyed, which implies you have to be balanced out, also known as the first law of thermodynamics. Heat is what we're going to be talking about for the most part in this unit, heat and enthalpy. Heat is, of course, two systems with different temperatures that are in thermal contact will exchange thermal energy. It always flows from warmer to cooler, so always, there's no exception to that. It'll flow from a warmer to a cooler object, and the reason is because it's a measure of energy. It reflects the motion of particles. Okay. Temperature is proportional, we just said that. That goes back to the heat 'em up, speed 'em up, as we saw previously. Someone even wrote down cool 'em down, slow 'em down. Someone wrote that on their test. Or I thought, maybe it was another class. I thought that was cute. Enthalpy, this is mostly going to be this unit on enthalpy, and then we will revisit enthalpy when we get to thermodynamics next semester. So you'll have to remember this. But enthalpy is the flow of energy. It's a heat exchange at constant pressure when two systems are in contact. There are several different types of enthalpy. There's the enthalpy of a reaction, which is basically what it sounds like, and that is the amount of heat released, which would be negative, or absorbed, which is positive by a chemical reaction at constant pressure. Our enthalpies are going to be mostly in kilojoules per mole of reaction. Heat enthalpy of combustion, basically the same thing as a reaction, except we're combusting it. Okay? The enthalpy of formation, put a star by this because this is going to be important. The enthalpy of formation are published values that I'll give you a chart, not all of them, but I'll give you a chart with some of them. But here is this is what I kind of alluded to in the beginning of the year when I said you're going to have to balance equations with fractions, because it is for forming 1 mole of your product from the constituent elements. So it will always be forming 1 mole. So for instance, that means if we were doing forming water, we would have H2 plus 1/2 O2 yields H2O. Because normally we balance that as 2, 1, 2 for water, but the enthalpy of formation is defined as only producing 1 mole of product. So you put whatever fraction coefficients you need to do for those reactants, okay? All right, that one I just want to reiterate, because that one catches people on tests every time. They start using the values and they forget that the enthalpy of formation is for 1 mole. So you got to use that the stoichiometry accordingly, okay? Enthalpy of fusion and enthalpy of vaporization, that's what's going on at your phase changes. And so the enthalpy of fusion is the heat absorbed to melt or overcome the intermolecular forces. And when we're melting things, we're not breaking the bonds, we're breaking the intermolecular forces. And it's the energy that is absorbed to melt 1 mole of solid to liquid at the normal melting point, okay? Here's what trips a lot of people up. If I am melting something, well, let's just go it this way. What is the melting point of ice?
0 degrees Celsius.
Did you just use the F word in here? Fahrenheit?
I didn't say the F word.
Oh, yes, you did. You said Fahrenheit.
I just said 30.
She applied the F word of Fahrenheit. No, 0 degrees Celsius is the point at which ice melts. When does water freeze? 0 degrees Celsius. So the enthalpy of fusion would be the same value as it would be for freezing. You would just change the sign. So you might want to make a note of that. Also, freezing, change the sign. Okay. Same thing with heat of the enthalpy of vaporization. The enthalpy of vaporization is the heat absorbed to vaporize or boil 1 mole of liquid to a vapor. So it would be exactly the same for condensing. You would just change the sign of that delta H. Okay. So just make note of that, because freezing point and melting point is the same thing. It just depends on whether you're going solid to liquid or liquid to solid. Okay? Boiling point and condensation point, same point, just depends on which direction you're going. Yes?
So is one direction always positive and one's always negative? Or is
Yes.
it dependent on what the probability is?
One direction is always positive. Which would be positive? Well, you tell me. Which one would be endothermic or exothermic? No, I'm going to lead you to I'm leading you, Adam, to this. Okay? So, in order to boil water, what do I have to do? I need to put energy into the system. So I'd be adding energy, so the system would be absorbing energy, right? So delta H would be positive. Okay? If I am condensing it, if I've got steam and I want it to go back to a liquid, what does that system have to do to that energy? Has to release it. So then delta H would be negative because exothermic is releasing, right? Okay. That was a very good question.
Great question.
Okay. So speaking of the system is the area of the universe we are focusing on, i.e. the experiment. Everything else is the surroundings. Okay. Endothermic is the net absorption of energy. You guys already know this from Chem 1, meaning the system is going to be absorbing energy, and delta H will be positive. Think of the good old baking soda and vinegar, bubbles and fizzes, and it gets really, really cold, and that's because it's absorbing energy from the surroundings. Exothermic is a net release of energy, and so it's going to be a negative delta H. I'm going to talk about entropy and Gibbs free energy just very quickly here, because we will not do it until thermodynamics, but just in case it shows up in one of the questions. Entropy is the measure of dispersal of matter and energy, and chaos or disorder is another way to say it. If you are increasing your dispersal, then it's a positive delta S. and it's a negative if you're decreasing. Gibbs free energy is going to be delta G when we get to it, and it will tell us whether we are thermodynamically favored, okay? And then, of course, thermodynamics is the study of energy and its interconversions. Almost done with the definitions. I told you there's a lot of definitions. Work, force acting over distance in physics, often expressed as work is equal to negative P delta V, where gases are involved, and we're going to express that in either joules or kilojoules. Standard conditions, this is new. We're used to saying STP, standard temperature and pressure. Standard conditions is different, okay? Standard conditions is, if I were in a lab doing this, what are my standard lab conditions? And it is 1 atmosphere, and it is 25 degrees Celsius, which is basic room temperature if you've got a good air conditioner. And if we're dealing with a solution, standard conditions are going to be 1 molar, okay? All of this information is communicated when they put the symbol, the little naught sign, like a degree sign, but a naught. Like, so if it says delta H naught, that means you're at standard conditions. So now you know what pressure, what temperature, and what concentration you're working with. They will give you that sometimes, and then you'll go, they didn't give me any information. How do I know what temperature I'm at? How do I know what that? But if you see that little naught sign, that's your clue as to what it is, okay? If you don't see the naught sign, then you're not at standard conditions. Okay, I didn't even mean that to like something. Okay, this last part, I just want to make note of this. If you see some older print materials, used to be for delta H, they just said kilojoules per mole, or sometimes they would just put kilojoules. But now, a couple of years ago, they wanted it expressed as kilojoule per mole of reaction. So you need to put kilojoule per mole. If you don't put the RXN on there for reaction, that's usually okay, but you want to do kilojoules per mole, not just kilojoules. So some of my old keys might actually say kilojoules, because that was basically at the redesign that they changed it. And so some of my old keys may just have kilojoules, but I've tried to go back and fix them and say per mole of reaction. Okay? All right, energy and work. Energy we, of course, define as the ability to do work. Here's our equation. Delta E is equal to Q plus W, heat plus work. If heat is being absorbed, Q is positive. If heat is being released, Q is negative. And here is an example of going in or out of the system and what it would be. So if energy is released to the surroundings as heat, Q is negative in this case. Q is positive in this case, being absorbed from the surroundings into the system. In terms of work, when we're talking about work, we're going to be talking about gases, and it will either the gas will either compress or expand. Okay, if it is being compressed, work is being done on the system because I've had to put energy into it to get it to go smaller. So work would be positive. If the gas is allowed to expand, it's doing work on the system by the gas. So W is negative. Okay. We're going to use this as a function of pressure, and so we'll use work is equal to minus P delta V. Okay, so you can see there if I am expanding, my work would be negative, and then a negative times a negative, work would be positive ultimately at the end. Or, yeah. Okay. All right, let's do the first problem. Got through the definitions. Done. Any questions over any of that definitions? They were all pretty straightforward, just some things I wanted to reiterate or focus on. Okay. All right. So calculate the work, the delta E, or the energy for endothermic process. So as soon as I see that word, what do I tell myself? Q is positive, in which 15.6 kilojoules of heat flows, and where 1.4 kilojoules of work is done on the system. If work is done on the system, what is W? Positive. So we're just simply going to plug in those numbers. Q plus W, 15.6 plus 1.4 is 17.0 kilojoules. Why did I go ahead and include the 0? Yes?
So why do we denote it as delta U in physics but delta E in here?
Difference, I really don't, I don't know the answer to that. I didn't know it was delta U in physics.
Okay.
To me, E makes sense for energy.
Yeah, they're both energy, but I'm wondering why.
Yeah, I don't know. Just difference in the way physics. Like another example of that is in chemistry, we call frequency V, the little funny V, nu, and y'all actually use F for frequency in physics. But in here, if you look at it, it's C is equal to the lambda times nu, and I don't know why. I think the F makes more sense for frequency than the V, but I think E makes more sense for energy. Okay? Exercise 2, calculate the work associated with the expansion of a gas. So when I see expansion, W is going to be negative because we're going from 46 liters to 64 at a constant external pressure of 15 atmosphere. So this is where we're going to do work is equal to negative P delta V. We've got 15 atmosphere. 64 to 46 is 18 liters. We need 2 sig figs here. So it would be negative 270 liters times atmosphere would be my units. Okay? And then I think that brings us to exercise 3. You can leave it here. It's asking you to calculate work, so you can leave it as liters times atmosphere.
Okay.
Yeah, you can leave it there that way. Well, it's not, yeah. It was asking us to calculate work, not energy.
Well, I know, but it'd be joules.
Well, you can put it that way, or you can leave liters atmosphere. Either one is fine. You would have to do a conversion factor, though. You can't just change liters times atmosphere to joules.
Oh, okay.
Conversion factor is 101.3 joules is equal to a liters times atmosphere.
That makes sense. Perfect.
So I would leave it as liter times atmosphere. It's easier. Okay, so we have a balloon being inflated. Okay. In the final stages, the volume of the balloon changes from 4 to 4.5 times 10 to the 6 by the addition of some energy as heat. So Q, we added energy, so we know that Q is a positive here. And then we gave delta V, we changed volume. So delta V is 0.5. We're going to leave it at that, 0.5 times 10 to the 6 liters, because we can do that in our head. So we're going to take our delta E is Q plus W, right? And we're going to substitute, we've got a Q, and then we're going to say plus P delta V. We're just going to do it all at one time. So that's 1.3 times 10 to the 8th joules plus, and then that would be a negative, what was our pressure? Oh, 1 atmosphere, yay. And then 0.5 times 10 to the 6 liters atmosphere, and then we're going to throw that conversion factor in there. 101.3 joules is 1 liter atmosphere. I have 7.9, but they have, when I did the calculation, but the answer key I think says 8.0, so I don't know which one it is. I wrote down 7.9 when I did it in my calculator. So, but the answer key in the notes says 8.0, so I may have not rounded correctly, which is 8.0 approximately. I don't know why the difference. Ah, stop.
Yes.
Okay,
Oh, it's more.
so that's going to take us to Hess's law and enthalpy. Actually, we're just going to mainly talk about enthalpy, and then we'll do Hess's law more tomorrow. Okay, enthalpy, we said in the beginning of the notes, is the flow of energy or heat exchange at constant pressure when the two systems are at constant contact. When we are measuring enthalpy, we cannot measure it directly. We can only measure the change in enthalpy, the difference between the potential energies of the products and the reactants. So this is one graph. It is either exothermic or endothermic. I want us to look at it and tell us what you think it is. We have the reactants, and then we have the products. So which is, the products have less energy than the reactants. Would you expect this to be an exothermic or an endothermic? He's saying it back there, right? It is exothermic. Yeah. So this is exothermic because we are losing energy. Okay, so next to that, I want you to go ahead and draw what endothermic would look like. Flip it around. So endothermic is going to look like this. Because the reactants absorbed energy, your product should have more energy than your reactants. Because they like to put those graphs on there. So recognize. I'm not putting all the other stuff in there. Just flip the switch. Okay? So when we are looking at enthalpy, there are several ways it can be calculated. We can calculate it stoichiometrically through calorimetry, which we are going to talk about here in a second, which is also going to be our lab for this unit. We're going to do a calorimeter lab from tables from the standard values that I'll give you or in your book, or you can look them up online. Hess's law and bond energies. Okay, those are all different ways we can calculate enthalpy, and you should know how to do all of them. Okay, so we'll do the easy one first, and that is stoichiometrically. Okay, upon adding solid potassium hydroxide pellets to the water, the following reaction takes place. We're making it aqueous, and then we have plus 43 kilojoules. So first question is, does the beaker get warmer or colder? Warmer. Why? Because this is what kind of reaction? Exothermic, because it's a product. When you have heat as a product, it's exothermic because it's being released. So it does get warmer, so that answers that question. And then what is the enthalpy change for the dissolution of 14 grams? Okay, so we're going to do some stoichiometry. 14.0 grams of KOH. And molar mass of KOH, I think is 5611. I'm going by memory there. Yep, 5611 grams per mole of KOH. And then negative 43 kilojoules per mole. Because when I write it as that, that means I need to remember that delta H is negative now. So when I'm going to use it as a calculation, I better make it negative. That's probably one of the most common things missed, is they pull it out and say it says 43 in there, but that's as a product. When you use it as a value, it's negative. Okay, so make sure you do that. And so then just good old stoichiometry, and it's negative 10.7 kilojoules per mole of reaction is your answer. Yes?
Why is it negative?
Because it's exothermic. Defined exothermic reaction has a negative delta H. Endothermic is positive. Yeah. So the fact that it was a product showing us that it is an exothermic reaction, that means when we use it, we write it as a negative value. Okay? If it had been a reactant, we would just use it as the positive value. Yeah. Okay? Any questions on the stoichiometric way, the easy way? Because if not, we're going to go straight into calorimetry now. Calorimetry is the process of measuring the heat based on observing temperature changes. We are going to be, there's several kinds of calorimetry, but we only have the capacity at this level to do coffee cup calorimetry, which we're literally going to be using styrofoam coffee cups, okay, because they are insulated, right? So they will minimize the loss of heat to their surroundings. And so basically we use the cup, we put the reactants, we start out at the standard temperature, and then when we add the stuff, when the reaction happens, we measure the heat difference, and we can use those, the change in temperature, knowing the specific heat and all that stuff, okay? And so we refer to this, because we're doing this in the lab, we're at constant pressure, it's called constant pressure calorimetry, and at constant pressure, Q is equal to delta H. I would highlight that or underline that of some sort, because it's important. At constant pressure, Q is equal to delta H. Okay, and those conditions would be constant pressure. Okay, our thing is going to look a lot like that. Actually, we have some calorimeters that are metal, but for the lab we're doing, it's just as easy to put them up as coffee cups, so we're going to do that. We're doing that Monday. So terms to know is heat capacity, which is the energy required to raise temperature by 1 degree. Joule per 1 joule. Specific heat capacity is specific to the material. Okay, Okay, everything has its own specific heat. Water has a very high specific heat. Metals have very low specific heat. In a nutshell, what specific heat tells you is how quickly or how slowly something will heat up. If it has a really small specific heat, it heats up really quick, but it also cools down very quick. So metals heat up very quick, but they also cool down very quick. Water has a very high specific heat, so it takes it a long time to heat up, but it also takes it a long time to cool down. Hence why your swimming pool will still be able to be swimming once it turns cool for a while. It takes a while. Or first warm day, all of a sudden you want to go swimming and you get in and that pool's still really cold because the high specific heat of water means it takes it a long time to heat back up. Okay. The specific heat is the quantity of heat transferred over the grams of material times the degrees of temperature change. Molar heat capacity is very similar to the other one, except that it's specific to 1 mole instead of a gram. And I will tell you right now, this will trip some of you up because you get so used to using the specific heat capacity that when it says molar heat capacity, you don't realize I can't keep it in grams. I got to change it to moles. Okay, so I wrote that in red. I don't even think that's in your notes, so you might want to write that in. Don't forget to convert to moles if you have a molar heat capacity, because that's one that trips people up. I promise I'm not trying to be tricky. That's what they do. So then that, the specific heat of water is actually like 4.184, which is really, really a fairly high one, okay? This is the MCAT equation. I don't know if it's a different equation in physics or the same one. MCAT, okay, they didn't change any parameters or things, yeah, not parameters, but symbols. Okay, MCAT, and it is T final minus T initial, okay? Bear that in mind, okay? And then water, of course, we have said that has one of the highest specific heats. But here's the part I wrote in red. I think it is in your notes, but circle it because this is where people get confused. The heat that is lost by the substance is going to be equal to the heat gained by the water. So what we're actually going to be measuring when we're doing this is the change in the water in our calorimeter. And then we'll say that that amount of heat or joules is going to be equal to the other one. So if the temperature increased, meaning it absorbed, then the heat gained by the water is positive, but the heat lost by the substance would be negative. So you just got to change the sign, but it's the same magnitude or numeric value, just different sign. Okay? All right. So now let's work some problems. Oh, there's your units of energy that you might see.
What is the box?
What box? Oh, those are supposed to be bullets. But whenever I bulleted it, it did it that way instead. Those are just bullets. I don't know why when I copied it from here to my PowerPoint, it changed my bullets. Those are weird bullets. They're like check boxes. There we go. This is what we'll do. We'll check them off. Calorie. There, we checked them off. Those are, now we know our units. All right, experiment number 5. We have a coffee cup calorimeter. We have 100 mils of 1 molar of sodium hydroxide. We have 100 mils of 1 molar HCl. Both solutions were originally at 24.6. After the reaction is complete, the final temperature is 31.3. Assuming that all solutions have a density of 1 gram per centimeter cubed, which is the same thing as 1 gram per milliliter, and we're using the specific heat of water because 1 molar is fairly dilute, so water is going to take over any of that. Calculate the enthalpy change for the neutralization, assuming that no heat is lost. So we are going to use Q is equal to MCAT, right? Okay, so we know that is 4.18 for not grams, joules per gram C. Let's go get our delta T up here. Final minus initial, 31.3 minus 24.6 is 6.7. So we'll plug that in. Now we need a mass. It's 200 grams. How did I get that?
You added the milliliters and
Yeah, because grams per milliliter means it's 100 grams of each one, so 200 grams total.
What if the molarity was different? Would you have to take that?
No, they're telling you what the density is. The molarity, it doesn't matter here.
Okay.
It's mass. We care about mass. Yeah. Okay, and so we all plug that in, and we get Q is equal to negative 5606.56 joules, and it didn't really tell us, but we usually do Q in kilojoules, so we're going to go ahead and put it in kilojoules. 1,000 joules is 1 kilojoules, just because that's the typical. So negative 5.6 kilojoules per mole of reaction. Okie dokie. Let's do another one. Everybody had that before I hit the next button? Okay, speak now or shut up. Just kidding. This one, let's do a different color. Let's do purple. Okay, now we have 1 mole of methane is burned at constant pressure, and we have 890 kilojoules per mole of energy is released. So that means that it is negative 890. When you see things like that, it's not a bad idea to go ahead and immediately write it so that you don't accidentally use it as a positive value. Calculate the delta H for the process if 5.8 grams of methane is burned at constant pressure. So this is a stoichiometric calculation. Okay, so 5.8 grams of methane divided by the molar mass of methane, which is 16.05. And then we'll use our delta H value, negative 890 kilojoules per mole. So it would be negative 320, forgot the 3, kilojoules per mole of reaction. Because remember, at constant pressure, delta H is equal to Q. Just remind you all of that. And this was constant pressure. One more, and then we're stopping for the day. Actually, just kidding. I want y'all to work that one on your own and see if you get it. I have a work on your own note myself. Okay. Okay, any questions before we stop for the day? All right.